Again, welcome back to day number 2 of the hands-on workshop on networking topic. I'm Jorge Crichigno, one of the organizers here from University of South Carolina. And I want to briefly go over the agenda for today, and then we will start with our first presentation. First, some updates in the website of our workshop. We have all the presentations, day number 1, also day number 2. And also we have the video, the recording of day number 1. For day number 2, the agenda is we'll talk about BGP. We'll have a first presentation on BGP and R&E Networks, followed by a hands-on session, essentials of BGP, EBGP, IBGP, initial configuration. We will have, again, our breakout rooms. We have 6 rooms. And then a second hands-on session, local preference and MET attributes, also about BGP. And a final presentation about network security, BGP security. So that's the program for today. I think we are ready for the first presentation. And I will introduce our first presenter, Brina May. Brina May started working on campus networking for Colorado State University as an undergrad and grad student. She then became a network engineer for the University of Denver in Colorado. In 2019, she began working for Arapahoe County government as a senior network engineer, designing, implementing, and supporting county networks. Brina is currently a network system analyst for the international network teams at Indiana University. So Brina, I will let you continue from here.
Perfect, thanks, Jorge. Let me go ahead and share my screen. Everyone can see my screen?
Looks good, Brenna.
Looks good.
Perfect. Well, hi, everyone. Again, my name is Brenna Mead. I'm with International Networks at Indiana University and EPOC. EPOC is a partner for this workshop. And today I'm going to talk about BGP and R&E networks. So we're going to go over some basics of BGP and how R&E networks differ from commodity networks and some of the networks that those of us are used to at our homes or at other businesses. And then later today, Hans Adelman, also from the EPOC team, will go over BGP security. So today is a day of BGP, so get ready and we'll get started. So today I'm just going to go over what EPOC is, a BGP overview, R&E routing, why it's different and why it matters, mechanisms for steering BGP, and a real world example. And then at the end, I'll leave some time for questions and discussion, as that was some of the feedback from last week, more time for some questions. So if anyone has questions, feel free to put them in the chat or save them till the end and we can have a discussion at the end. So EPOC Engagement and Performance Operations Center, it's a joint project between Indiana University and ESNet. So we create partnerships with regional infrastructure and science communities that span the NSF and DOE. So we have 5 focus areas: roadside assistance, consultation, application deep dives, network analysis, services in a box, DMZs, personas, etc., and training. So today we'll be focusing a little bit on that training section and also going over routing within the R&E community. So we're going to start out with what is BGP? BGP, or the Border Gateway Protocol, is a protocol used between routers to exchange information and reachability information between or inside ASs on the network, so on the internet. So BGP makes the internet work. I know that seems ridiculous as an overarching statement, but it is true. And in most cases, it just works. However, we find in many cases, especially in R&E, that it needs to be tuned for the best performance. BGP makes routing decisions based on paths, network policies, rule sets, etc. Later, we are going to go over how BGP makes those routing decisions and how you can tune your BGP to perform the best for your data transfers or for whatever type of network needs and use cases you have. Something else that's important to know as you talk about BGP is the AS number. AS stands for Autonomous System. It's used on the internet to identify networks and systems. It's a collection of prefixes or routes under the control of one or more network operator under one administrative entity with similar common routing policies. So for example, Transpac, which is run by International Networks at Indiana University, has an AS of 22388. So that is how it's identified within BGP when you use show IP route. It used to be a 2-byte number, however, we needed more. So now it is 4 bytes. In the 90s, we had less than 100K AS numbers on the internet, and now we have over 100K. Some of these spaces are reserved for private use. And as time goes on, we expect more and more AS numbers to start appearing on the internet. So I spoke earlier, we have R&E networks versus commodities. So many of us know what a commodity network is. It's the internet used for a company or a business. It's your internet service provider. It is Google, it is Amazon. Instead of commodity, we also have R&E networks. So that would be things like your regional network. Many of you are from universities that connect to a regional network, whether that's GPN, FRGP, iLight, NYSERNET, Internet 2, ESNet, GÉANT, which is the network connectivity for European science networks, and then also European NREN. So all of these fall under the larger umbrella of R&E networking. And there are differences. There are many commodity networks, and there's many research and education networks, but they have separate purposes and different tuning that can be done for better performance. So what makes our R&E architecture different? R&E networks are engineered specifically for science traffic. We want to keep R&E traffic on R&E paths if possible because they traditionally have higher bandwidth, performance engineering to create the best possible data transfer performance. And we determine the behavior of these routes, and making performance better on R&E paths than often on commodity routes. In order to have the best performance on R&E networks, we all have to do our parts. All routing decisions have to be made locally and with intention, and emergent behavior is also important. So noticing what happens in reality versus what we expected routing to do. So what do we do? On a high level, we need to use BGP policy to keep R&E traffic on R&E networks. So we do this through BGP announcements to attract traffic. Routing determines the path the traffic takes through the network. BGP gives us the tools to determine that path. BGP is a path vector protocol. So the shorter AS path is preferred. And I will have a diagram in a few slides to make this concept a little bit more clear. But as with many things in life, the internet is going to choose the shortest path naturally. If AS path length is the same, then other criteria are used. And later we will go over the BGP path selection algorithm and go over how some of those other decisions are made when AS path length is the same. In order to do some performance tuning, it's often necessary that we have to override BGP's use of AS path length when choosing between R&E and commodity paths. Often, the path length algorithm will choose a shorter path that includes commodity over the better performing high bandwidth R&E path. In most cases, the R&E path is longer. So based on just AS path length, BGP and the internet will try to choose the commodity route. So remember, hop count is a legacy metric. And so some of the things that we're going to go into as this presentation progresses will be how to tune that legacy metric to work in your favor. So why does this matter? This example is from the Ohio Supercomputing Center to NERSC. So These are very common data transfers between the supercomputing center and NERSC. And the EPOC center was seeing very slow performance on data transfers between these two locations, below 60 megabits per second. We were expecting to see closer to 10 gigs, so 60 megabits per second is very poor performance. It turned out, after a little bit of engineering and deep diving into BGP policy, an out-of-date BGP policy was causing traffic to pass over the commodity instead of the R&E paths, going both directions. So sometimes we'll see in cases that a route is asymmetrical. So in one direction, it will take the R&E path, and in the other direction, it will come back the commodity, which does also affect performance. But in this case, it was taking the commodity path in both directions, significantly deteriorating the performance that we expected to see between these two data transfers. Commodity networks often throttle high-speed flows. In the world of Comcast and CenturyLink, a large significant traffic spike means a DDoS attack. But in R&E, it just means that scientists are doing what they're expected to be doing, transferring data between each other at high capacity and high bandwidth. So what's next? In order to control BGP, we need to know how to manage it. So BGP just works, but as I said earlier, it needs to be tuned for best performance. Best path selection is a 10-step process, or can be. So I'm going to go over 4 common steering mechanisms today, but also to the right is some other steering mechanisms that are used that I won't be discussing. So we have AS path, origin type, MED, EBGP, IBGP, which we will go over a little bit in the hands-on exercises coming up, network exit, age of route, router ID, and neighbor IP. So these are many of the ways that we can steer BGP for best performance, but we're just going to go over local prep, communities, AS padding, and MEDs. So the first way that in BGP we can help the network choose the R&E path is local preference. So this is per prefix in BGP. It modifies the path for your outbound traffic. So if you change your local preference to higher than another, then it will choose that path. So in this example, the local preference for the commodity network is 100. And we set the local preference for the R&E network at 200, meaning this traffic will take the R&E network because of that change in prefix or addition. An additional way that's becoming fairly popular throughout, especially in the R&E community, as these networks grow and become more performant, is BGP community strings. So a community string is a number. It's almost like a tag. So we're tagging these prefixes with communities, telling the peers how to handle the prefixes in a special way. So this allows us to make changes to routing policy based on the per prefix strings. And prefixes can have multiple community strings, just like anything can have multiple tags. It just provides information about that prefix and what decisions should be made based upon that community string. Communities that might be useful to external networks should be public. So this provides a mechanism for peers to affect a network's internal behavior. Some common uses are changing their local preference or DDoS mitigation. So what you want to do as a network engineer working with BGP is look for upstream network published communities. So that may be regional or national. We're going to go over some of the community strings that Internet 2 uses in order to give us more information as routing decisions are made. So for example, public BGP community strings offered by Internet 2. If you click this link, the slides are available on the agenda. There are quite a few more listed BGP community strings. I just decided to pull these out as examples. So set local pref on your advertised prefixes. So the default is 100. So in this example, 40 is low and then 160 is high. And the prefix identification, so we have our ASN and then we have 5004, which is Amazon. You can also add where does the prefix enter the network. So for this network, it's 242, New York. You can also use it to indicate emergency. So here we have 911, which would discard all the traffic destined to that prefix. We will later go over AS padding, but this is another example, is you can prepend your prefix to make your path longer using these community strings. So as I mentioned earlier, AS path is a legacy metric. So it's how BGP usually just makes the internet work. So as you can see from this diagram, BGP and the normal workings of the internet are going to go from campus 1 to campus 2. Because this AS path length is 3, they're going to want to take this commodity provider, which is only 10 gig, and again has some of those commodity settings that will affect your data transfer performance, such as DDoS mitigation and window sizing and jumbo frames. So we want to take this path, which is again longer, but has higher bandwidth, 100 gig connectivity throughout the regional 1, internet 2, back to the regional 2, and then over to campus 2. And so in the next slide, we'll show you how to sort of mitigate this using AS padding. So again, BGP will choose the shortest path. So something you can do is AS padding, which essentially just adds more prefixes to your path so that it picks, so that it doesn't pick a certain path over the path that has the shortest. So in this example, you can see we added this ASN 133465 3 more times to make the path longer so that this is no longer the preferred path. Multi-exit discriminator is another way that we can help BGP make decisions. So this is useful when you have N+1 connections in your network. It's an indication to external peers of the preferred path in your network. And again, the lowest number is preferred for this case as well. So by doing this, you're indicating that this regional 1 over here is your preferred path into the network, just by setting these 2 figures. So what are the takeaways of this BGP talk? Routing will not take care of itself. Yes, BGP just works. In most instances, especially over commodity networks, BGP just works and it does what you need to do to surf the internet or be productive on the internet. However, in R&E networks, it doesn't always perform as expected because R&E networks are tuned to perform for data transfers specifically for science use cases. So often old routes that have been there for years may not work well with new networks as new networks come up or are changed based on changes in equipment or increases in bandwidth connectivity. In addition, we've seen throughout the R&E and international community that often new routes may not work as planned, meaning that BGP does not adjust in the way that you expect to a new route or a new link on your R&E network or even overseas or wherever this new link may be. So something that we as an R&E community are trying to address is how do we address routing and performance as a community and have more efficient and better routing throughout the world. And so one of the initiatives that we have done recently is called the Routing Working Group, which is a collaboration of both domestic here in the United States and international NRENs and other partners to come together monthly and discuss ways to deal with routing issues and also to discuss best practices for BGP and other concepts within the routing community. So we have an engineering focus. We document possible erroneous or interesting routes throughout the world. We identify teams to address them, and then we check in together as a group to work through them. We have about 150 partners within this group, and we have over 15 cases of erroneous routes that we've worked on since the beginning of the Routing Working Group. Within this, as I mentioned, we are also looking to create some best practices for the R&E and international community. So this is a policy focus, better detailing of policies routing policies for paths, including preferred backup paths, verify if the policy is being followed, and also create best practices for policies going forward. Some of the examples of routing issues that we've seen within the routing working group are asymmetrical routing, which I touched on a bit, meaning a source to a destination takes one path one way and takes a different path when it returns to the source. I mentioned this is often an issue in the R&E community, as in one direction it takes the expected performant R&E route, and then on the way back it takes the commodity route, affecting the performance of that data transfer coming back to the source. Another example of cases we've seen is R&E data takes a less efficient route around the world, affecting performance. So Europe to Asia routes traversing the US instead of going directly towards each other. Africa to Europe routes traversing the US. Often these aren't necessarily bad. It's just important to confirm that the BGP again is working the way that you think it's configured to work, and just monitoring those BGP selections as they change throughout the world. Again, R&E taking a commodity route when an R&E path is available, and then new R&E links are removed or added, but routing does not adjust appropriately. So again, some of the goals for this routing working group in 2022, especially regarding BGP, is to introduce more routing cases and solve more routing anomalies throughout the world. Continue to provide tool talks, similar to some of those that you've seen at this workshop, and create a series of community-driven BGP best practice documents. So best practices for R&E providers specifically, and how do they differ from other networks? We touched on that quite a bit in this talk. Scalability, how do we scale up effectively and without affecting performance? Load balancing, R&E peering agreement best practices, and again, communities, how to use these with a focus on R&E networking. So if any of you have any questions about this presentation, BGP, would like BGP resources, or are interested in joining the routing working group, feel free. Two of the chairs are here on this, this class today, Hans Adelman and myself, Brenna Mead, and our emails are there. You can join the routing working group and you'll get on the routing working group list and be added to the monthly meetings where we discuss cases and where you can bring your own cases to be discussed by the community, or ask any questions that may be impacting you at your home institution. We also provide tool talks. Our next meeting will be a perf sonar tutorial based specifically on routing troubleshooting. So if that interests any of you who were in the perf sonar talk last week and would like to see how it's used to troubleshoot specific cases, feel free to contact us and we will get you added to the routing working group. Okay, and I would like to open us up for questions. If there are any, there may be some in the chat, so I will take a look quickly here.
There have been a few. I've been trying to answer them as they come in. The last one is from Michael Smith. He asks, are community strings in BGP similar to S&P community strings? And honestly, no, they're not, is my answer. So, and security is very different for both, Brenna, if you want to.
Yes, no, they are not. S&P community strings aren't really an identifier of a decision or what might happen along that path. You know, S&P community strings are just so that two devices can connect to each other and read information of each other or write to them. And that's not exactly what BGP community strings are. And I think Hans will touch a little bit on community strings in his security talk as well, but they are not the same.
And of course, if you have more questions, Brenna will be in the BGP breakout session after the first lab.
Yes, and I will also be here for the hands-on exercises in case any questions come up as you all work on it hands-on.
The question from Paul is, so is the combination of all these knobs more of an art or science, Brenna?
I think it's, in my opinion, it's more of an art. I think, especially in the R&E community, a lot of it is trial and error. Wow, this performance is not what we expected. What's happening? What's causing that? We have this science use case, and we're expecting X performance, X gigs out of it, and we're only getting, again, 60 megabits per second, like that Ohio State example. And in essence, it is a science because we are network engineers, but a lot of it is an art of what's the best path? What is the best option to change how this BGP decision is made? Is it AS padding? Is it community strings? Is it some combination of all of these systems to make peering better? And also, it takes a lot to actually see the problem and identify whether it's asymmetrical routing, traffic going over commodity link, traffic taking a route that you're just not expecting there, or that isn't performant. So it's, I would say, an art. And as we get better at it, and we develop these best practices that I spoke about the routing working group, we're hoping to push it more towards a science where we sort of all know exactly, not exactly, but have an idea of what the ultimate goal is and the best practices are with BGP. But again, because BGP just works most of the time, it lands sort of in the back of the head of many engineers. Well, the traffic got there, but it's sort of an art to see how it got there and whether that's the best performance it can get.
Michael asks, if our institution is not part of an R&E network, how do you apply? And I believe, Michael, you're Fayetteville. So you would want to contact the folks at the MCNC regional network. They're the ones that support North Carolina. And we can, of course, get you in contact with them. Oh, nope, never mind. Sorry, I Googled the wrong FT. Oh, good, perfect. I Googled the wrong FTCC.
Okay. Yes, we'll have
North Carolina.
And then we'll be covering route maps and route filtering with BGP in this session. I don't know about the hands-on session, but it's certainly something we could talk about in the breakout group, in the breakout session, if that's a topic of interest to those in the group.
Yeah, Brenna, and we will be covering a little bit of that in the hands-on session.
Perfect. Yes. Okay, well, I have 2 minutes left if there's any more questions. Hans, will you put my email in the chat just for contact info? And
sure will, yeah.
Thank you, everyone, for joining my presentation. And if you have any questions, feel free to email me, join the routing working group, or just put them in chat as the day goes along. And I'll be here all day.
Thank you very much, Brennan, for this great presentation. So Christy, I'm trying to share my screen. Would you mind letting me share so we can go through the next presentation? Okay, thank you very much. Well, briefly, we have 1 minute left. I just want to mention something Brenna was talking about, experience and the art of BGP. There is material to learn a little bit more about BGP. You will go through some virtual labs today, but there is much more. The lab library include quite a bit of BGP, and there are other libraries with advanced BGP topics as well. So those are available. Feel free to contact us and we will give you access. You already have access to the intro to BGP. That's something aside, and we will talk more about this in the breakout room. Now, the next topic, the next presentation or session is a hands-on session on BGP. So this hands-on session will cover essentials of BGP, what Brenna was talking, external BGP, internal BGP. So if you didn't register to the virtual platform, please feel free to do so. There is a link, enroll. So you just click there and we'll take you to the BGP lab library. This session will be by Ali Al-Sabeh. Ali is a PhD student here at the University of South Carolina. He earned his computer science bachelor degree from the Lebanese University. He then pursued a master's degree also in computer science from the American University of Beirut. And he is currently doing research on malware analysis using P4 programmable data planes. So Ali, I will let you continue from here. Feel free to share your screen and we can start this session.
Thank you, Dr. Jorge. I'll share my screen. I hope everyone can see my screen and can hear me well.
Yes, Ali.
Okay. So in this presentation, we'll go on a brief overview of our BGP lab series. What are the labs that we basically developed in this lab series? And as you can see here, our BGP lab series includes 10 BGP labs, starting from the very basic tools that we use, the Mininet emulator and FRR routing, all the way to advanced BGP features. And the goal of this lab series is to basically allow everyone, even someone with basic networking knowledge, to grasp a good BGP knowledge, starting from the basic configuration up to advanced configuration, such as configuring BGP attributes, route reflections, and so on. On top of these 11 labs, we have also 4 exercises. So once you complete a set of lab, you can test your knowledge by going and checking the exercises. And I will show later on the link for the website where all these materials are available. So this is just a overview. I'm gonna just go over it quickly as Brana was talking about BGP, and essentially the internet is basically organized into autonomous system. Within an autonomous system, IGP are configured, and each institution configures its own IGP. And to communicate between the autonomous systems, an exterior gateway protocol is used, and mainly the most commonly used one is BGP. So why do we need BGP? Why, a question here is, why do we need BGP when we have when we could have only interior gateway protocols? Every institution can configure its own, and basically IGPs they only care about moving packets as efficiently as possible from the source to the destination. So an example of IGP could be like an OSPF that delivers, chooses the route that has the least cost, or like RIP that chooses the one with the least number of hops. However, IGPs, not too many routing policies can be enforced in the network. For example, like a corporate autonomous system wouldn't want to allow traffic originating from a foreign autonomous system. However, telephone companies will want to carry traffic from their customers based on a subscription fee or other criteria. All these routing policies, they're not typically available in IGP, but they're much easier to be configured in BGP. The first lab that we're basically going to cover is an introduction to BGP. So in this lab, we will only configure the basic BGP configuration, and our topology is as follows. So we have 2 autonomous systems, network 1 and network 2, autonomous system 100 and 200. In each network, we have a router and internal network comprised of a switch and a host. And the aim of this lab is to show how we can configure BGP on both networks, in particular R1 and R2, so that at the end of configuration, I'm able to ping from host H1 to host H2. This is the end goal of this lab, to navigate over our topology, the tools that we use, how do we emulate these routers, switches using Mininet, how do we enable the routing protocols, and how do we configure them, and finally establish and connectivity. So for configuring BGP, we will use FRR, which is a routing protocol suite that offers like multiple routing protocols such as BGP, OSPF, static, and others. So for in this scenario I'm showing here, we have router R1 and we have this configuration. Let me highlight it. And as you see here, first I'm enabling the BGP daemon, of course, and then I'm entering the shell. I'm assigning an autonomous system to the router, and also I'm assigning a neighbor to this router, specifying its autonomous system. And I will go over like every step in details once I'm doing the hands-on session. But this is just a brief overview. Similarly, this same configuration, I will do it on router R2. I will establish a BGP connectivity between R2 and R1, assign a BGP autonomous system, so on. Now, once the BGP neighborhood is established between R1 and R2, I'm gonna go ahead and advertise the networks. So for example, on R1, I'll be advertising network 192.168.1.0 so that router R2 knows about it and be able to connect to it. And similarly on R2, I will advertise its internal network 192.168.2.0/24 so that R1 can know about it. And after that, after configuring BGP, we will also show the routing table of the routers and see how the entries are now installed in the routing table, how they are learned, through which protocol they are learned, and how they are reached. And finally, we will establish, test the connectivity between host H1 and host H2. We will also show the BGP table of the both routers. We'll also demonstrate like what is the difference between the BGP table and the routing table. And from here, I'll go on to the hands-on session. And I will go start from our website, just to show you how do you get access to the hands-on session.
Ali, in case that, Ali, just a second. Do you want to share the URL of the website in the chat window? So in case somebody want to just follow from there.
Yeah, absolutely. So I will copy the link of the website and I'll paste it in the chat. So this is the link of our website. And if you see here, this is day 2. And this is the hands-on session, session 3. You can check the PDF, the PowerPoint and the PDF. And also you can enroll. If you click on the enroll button here, I will copy the link. And just paste it here so that like I will show you what happens once you, if it's the first time that you basically log in to the NetLab or NDG portal, you will have the option to register or log in. I already have an account, so I'll go ahead and just log in. I think I copied the wrong one. Okay, so once I log in, because I'm already enrolled in the BGP one, so it will pop up here. If you're not enrolled, you will have the option to just like automatically enroll, just like 1 or 2 clicks, and you'll be able to see it. So for this hands-on, I'm gonna click on the workshop on networking topics, BGP. And here, you will see the set of all BGP labs as well as the exercises. So for this hands-on, I'll be configuring lab 3. So it's introduction to BGP. I'm highlighting it. I'm gonna go ahead and click over it. Here it just like takes a little bit just to load the pod and get access to the actual content of this lab. So I'll be waiting for the. Sometimes it takes time, especially if there are like multiple people that are basically accessing it at the same time.
Yeah, and Ali, while you are doing that, do you want to share the cyber training website where all the lab manuals are located?
Yeah, sure.
Because there are some questions about where can we access the lab manuals.
Yeah. So I'll paste the link also for all the lab manuals that we developed here at UofSC.
Do you want to show the BGP? I think it's at the very bottom.
Yes.
In case somebody want to download that.
This is our BGP library. I sent the link for this page on the group chat, and here you can see all the BGP labs that you have. If you click on the PDF, you will see all the labs and like one single PDF, all the 10, 11 labs as well as their exercises. This is like the content, you can go over them.
And also we put online for the BGP lab series, the VM, because we only use one virtual machine for the BGP lab series. So in the workshop website, website, you will find the VM. So there is a link. Just keep doing over there. So that's the virtual machine.
Yeah, so if you want to have your own like virtual machine on your laptop, you can install that and you can test the labs. So I'll go back to see if, okay. So now once I clicked on lab 3, introduction to BGP, I'm already in the pod. So here you see the topology. The topology only is our BGP labs run on a single client. So this is like the only machine that we're using. The second tab over here basically includes the content of the lab. This only includes lab number 3 because we clicked on it. You will also see the client here, which includes the virtual, like the environment that we'll be using to configure the BGP lab series. Okay, so now I'm gonna go back to the content here. I'll be splitting the screen into 2. The left side will include the content and the right side will include the virtual machine. So if you click here on the like small down arrow or open a new window, I just get here to the, and then I will click here on the client, and this is our virtual machine. I'll just like improve the quality of the screen just so that everyone can see it better. Or if you can, if everyone can see it, I'll keep it like this. Okay. So I'm just like scrolling over the BGP. Here you see the content, lab content. Moving on, you'll have like an overview of our lab, what we'll be doing. And this is the lab settings. The lab setting includes the username and the password. The password is password, which we will be using to like execute some commands that requires like higher privilege. So we'll keep that in mind. Moving forward, the first section in every lab that we developed always include an introduction to the topic that we're basically discussing. So in this example, we're introducing BGP. And the idea here is that every lab is self-contained, so that if you don't have any idea on BGP, you don't have to like go to external resources. You can just like read the introduction, and you should be good configuring the lab, understanding it, and get an in-depth view on it. So I'll just skip over the introduction and go immediately to the hands-on session, which starts from section 2. So this is our topology. Sometimes it just loads. And the first step is basically, step number 1 is launching mini-edit. Mini-edit is just like a GUI of the MiniNet emulator, which allows us to emulate like hosts, routers, switches, and so on. So I'll go ahead and double click on mini-edit here. Okay. And here it will ask for a password because mini-edit requires a password. And as we said before, the password is password. So once we click on mini-edit, it will open a window here, and you will see 5 icons. This resembles the host, switch, router, and the link. And if you want to play with it, you can build your own topology, emulate your own network. You can do many things using MiniNet. So in this lab, we don't build our topology from scratch, but rather we just like load it, so that like we don't waste time building it and configuring everything. So in order to the topologies are all like saved within each lab directory. So to load them, I will click on the file here and then open the second one. You will see here the set of labs. In my case, I'm in lab number 3. So we'll click over it and then select the mn.mn file, which is our MiniNet topology. Double click on it. So now at this point, I've loaded the MiniNet topology, and now before clicking the run button, what we have to do is, in this lab series, what we did is that we automate the process of configuring the IP addresses on the routers. So rather than like going into every router and setting the IP address on every interface, what we do is just like wrote a script that automates this process. So in order to run this script, I will open a Linux terminal, which is the third icon on the right here. I click on it. This is step number 3. And then I will navigate in step number 4. I will navigate to the directory of every lab, because every lab has its own topology, its own IP addresses. So the configuration file is different from one lab to another. That's why we separated them into different labs. This is change directory, lab number 3. And step number 5, we will actually call this script that we wrote and give it an argument, the IP addresses of our topology, which is lab3conf.zip file. So in step number 5, this is the script called config loader, just like writing tab to autocomplete it, and then lab3_conf.zip. Now, once I execute this command, the IP addresses will be loaded on the routers. So I will exit this terminal because I'm no longer using it. Exit. Now that the IP addresses are already like will be loaded in the routers, I will go ahead and start the emulation, mininet emulation. And to do that, I will click on the run button and the bottom left of the mininet screen. It's here. And once you click the run button, you will basically these icons here will be grayed out, meaning that now the emulation is started. Now, how do you like check the links and what are the components in your mininet topology? To do that, you can basically open the mininet terminal in step number 8. It's called shell number 1. And here you'll see this is a mininet shell. It's not like a Linux shell. To check the links of your topology, like what are the components that are connected, you simply write the command links. And basically, you will see every component and every interface of every like device connected to which one. So in this case, I'm having S1, ETH1 connected to R1, ETH0, and so on. You can validate for other devices. Okay. So now moving to the next step, which basically getting into every host and every router. What we'll do is go back to the topology. And now I'm gonna, in step number 1, I'll open a host terminal. So what you need to do is you need to right click, but you need like to hold the right click of the host terminal. So you have to hold it and then select the terminal. And now I'm in host H1 terminal. I will launch the command to verify the IP addresses because as I mentioned earlier, the IP addresses should be loaded on the host as well as the devices. So to validate that, you can write the ifconfig command and check it out. You will see that the IP address is 192.168.1.0 as expected, as well as the subnet mask and the loopback interface. Similarly, you can also validate the default gateway, like what is the default gateway of host H1, which in our case will be typically R1. So to do that, you will write the command route here. And it's like just take a few seconds, but it will eventually show that the default route is 192.168.1.1. As you see here. Okay. Similarly, you can repeat the same steps on host H2, validate the IP address, the default gateway, and so on. And this is basically in step number 4. Now moving to the routers R1, in particular router R1. You also, if you want to need to open a terminal on R1, you have to hold the right click on it and choose the terminal. And I'll just move it here so that R1 will keep showing the topology. Okay. So the essentially in every step in this lab series basically is loading the Zebra daemon, which is a multi-server routing software that basically provides TCP and IP routing protocols. And now, after you like launch the Zebra daemon, what you have to do is basically write VTYSH to enter to FRR shell. I'm just moving like fast just to show the routing table. Make sure that the IP addresses are all configured. Here we'll see like 2 entries install the routing table, which corresponds to this link as well as this link. 192.160 internal network 192.168.12.0 is directly connected to R2. And similarly, this is an essential step that you have to repeat it on router R2, which basically launching the Zebra daemon and going into the VTOISH session. If you show the routing table, it will have similar results. Now I'll move to the our main theme in this lab series, which is basically configuring BGP. We'll start off with on our router R1. So this is R1 here. And essentially, if you want to use any routing protocols using FRR, you have to enable its daemon. So now, and this daemon basically runs in Linux. It's not, so we have to enable it. In order to do that, I will go back one step to the Linux terminal, exit here, and I will enable the BGP daemon, BGPD. Now the BGP daemon is enabled. I will go back and enter the VTOISH session, which allows me to access the FRR shell. A step here that I will do also before configuring BGP is to enter the configuration mode. So if you write configuration and click the tab, terminal, now I'm the configuration mode. The first step in configuring BGP is assigning an autonomous system number. So in our case, the R1 is within autonomous system 100. So to assign this autonomous system, you will write router BGP 100, corresponds to the autonomous system number of router R1. Now I'll assign a BGP router ID to R1 so that like other neighbors will know it using this ID. And in order to do that, you have this command BGP router ID.
So Ali, just for a second, just momentarily, I see a comment here from David. I'm getting a PID log file error attempting to start Zebra. Are you familiar with that, or Eli?
That's I probably you're launching Zebra on the host H1. So we're only configuring the routing protocols on R1 and R2. So Zebra should be only loaded on R1 and R2 and not the host H1 and H2.
Thank you.
Okay. Yeah. So yeah, I was configuring a router RD on R1. So I'll write BGP router ID, and the ID is 1.1.1.1. The convention here is that like because I'm configured on router R1, I was 1.1.1.1. On router R2, I was 2.2.2.2.2, and so on. Now I will establish a BGP neighborhood with R2, which is an autonomous system 200. In order to do that, I will launch the command neighbor 192.168.12.2. On neighbor, now specifying the IP address of R2. Okay, and as you see here, just for any neighbor you want to establish a BGP neighborhood, you have this command neighbor. You specify the IP addresses connecting to it. Like in this case, even router R2 has multiple IP addresses depending on its interface. I'm establishing it using the directly connected link, which is 192.168.12.2. And you should also specify the autonomous system number of your BGP neighbor, which is in our case 200. You just write remote AS, stands for remote autonomous system 200. Now you can end the I'll just leave the BGP configuration mode by writing end. I'm still in FRR session by shell, by the way. I just exited the BGP configuration mode. Now I will launch the command show IP BGP neighbors, which verifies that the neighbor command that I previously executed took effect. So the command is show IP BGP neighbors. And as you see here, you'll see the neighbor 12.2, the remote, which is router R2. You'll see a remote autonomous system 200. You'll see also the router ID, but you will not see any packets sent and received between R1 and R2 because we haven't enabled BGP on R2 yet. So in the next step, we will do that. Okay, I will go to R2 and I will repeat the same commands that I did before, which is basically first exiting the terminal, going to the Linux terminal, enabling the BGP daemon, then going to VTYSH, accessing FRR shell again, going to the BGP configuration mode. And now for router R2, I'm in autonomous system 200. So I will assign, this is the autonomous system number. The router R2 ID of R2 is, as we said, BGP router ID 2.2.2.2. And you can now you will establish a BGP neighborhood with R1, which has an IP address 192.168.12.1, and it's an autonomous system 100. Neighbor R1 192.168.12.1. It's an autonomous system 100. You will also exit the BGP configuration mode. And now I will go ahead and launch the command BGP neighbors. So now I should be able to see some statistics. Here, once I launch the command show BGP neighbors, you will see the BGP neighbor is 192.168.12.1, which corresponds to router R1 here, specifically this interface. It's on remote autonomous system 100. Our local autonomous system is 200, external link. This is the router ID of our neighbor, 1.1.1.1. This is our local router ID. And you will see here that now there are some statistics that are being shared between both routers. Okay, so now we have established a BGP neighborhood between R1 and R2. So let's go ahead and check if there's a connectivity between both routers, or like between the routers and the host and so on. So on host R2 here, I will go ahead and ping 192.168.12.1. And this IP address corresponds to R1, especially this interface. As you see here, the connectivity is successful, and this is expected because when we show the routing table of R2, you will see that there's an entry for this network. So I will just like show it. This is of the lab. If you see here, the routing table of R2, you will see the entry here for network 192.168.12.0, and that's why we had a successful connectivity. But what if we try to ping host H1 from R2 or from host H1? Let's see what happens. So on the same terminal, router R2, I will go ahead and test the connectivity with host H1. Host H1 has an IP address ping 192.168.1.10. So here, as you will see, the network is unreachable. And even though we have established a BGP neighborhood between R1 and R2, there's an essential step that we haven't done yet, is advertising the networks. So in case of R1, we haven't advertised the network 192.168.1.0. So that's why the routing table of R2 doesn't contain anything related to 192.1.0. And similarly, if you try the same exact thing on R1, if you try to ping host H2, you will also get unsuccessful connectivity because router R2 did not advertise its internal network. Now, in the next step, we will advertise these networks, and we will see the modification that happens to the routing table as well as the BGP table, and we'll see if we will get any connectivity. Okay, so I'll go back to R1 terminal here. Click here, R1. We'll go back to the the command configure terminal. And now I will go ahead and enter the same configuration that I did before, the BGP configuration mode. And the autonomous system of R1 is again 100. Now, the command that I used before to establish a BGP neighborhood is neighbor. The command that you use to advertise the network is network. So in this case, I will write the command network. And here I will advertise the network, the local network of R1, which is 192.168.1.0/24. I can pause for like for a little bit if you want, Dr. Jorge, in case anyone has like question or if I'm going too fast. Okay.
So Anthony has a question. Do you have to issue the network, the command network IP, where the IP is the IP address of the network that you want to advertise? Do you want to do that? Do you have to do that for each network? This is my answer. You will have to do that for each, but probably there is a way to make more efficient. I will let people who have experience with this in operational networks. I don't know if you want to add something, Brina or Hans. What if you have to advertise so many networks, static networks that are attached to your network?
Usually you can do it through some type of route policy, right? Where you take routes from your IBGP or your interior, whatever you're using interiorly to route, whether it's that or ISIS or whatever, and push that into your BGP configuration. There will be some policy management, but it's not normal that you would need to type in, that much static stuff like this.
Thank you. Did you want to continue from here?
Yes. Okay. So now I've advertised the network 192.168.1.0/24. And essentially now after advertising, router R2 should know about it and should have an entry corresponding to this network in its BGP and routing tables. I will exit the BGP configuration mode. And now I will show the BGP table of R1. Show IP BGP. That's the command to show the BGP table. Let's move it a little bit. Okay. And once you write this command, there are like multiple information, some information that will pop up here. First, this include the version, BGP table version that we are using. What is the router ID, which we configured 1.1.1.1. This is the virtual routing and forwarding ID, which is 0 because we haven't established any virtual routing and forwarding. I believe in our advanced BGP and MPLS series, we have a lab on this. So if you also want to check it out, it's in our BGP advanced MPLS and BGP library. And here we'll see some status code that will, such as suppressed, in case the entry is not installed. Star means the entry is valid. The arrow here means that this entry is the best one, and this is the one that's that's used, because sometimes you will have multiple paths to the same destination, but only one of them will be used according to the BGP attributes. So this arrow here indicates which entry or which next hop will be used to this destination. So here we will see in the BGP table, we have the star and we have the arrow, which means that this route is it's in the BGP table 192.168.1.0/24. The next hop 0000 means that this route has been originated from the router itself. So because we advertised it, not this network, and not like we have received it from any other external network. So that's why the next hop is 0000. These are the metric and the local pref attribute we will talk about in our next hands-on session. But these are BGP attributes. This is also a weight BGP attribute, and the path I here, it just means IGP, but what it basically means is that it's in the same autonomous system. It has been originated in the same autonomous system. Now I will show the routing table of, I will go to R2 and show the routing table. Okay, we'll go to R2 here. If you launch the command show IP route on R2 again, let's see which entries has been added. Previously, we had these two entries in the routing table of R2. Now we have this entry loaded. And just before elaborating on this entry, once you write the command show IP route, you will see multiple codes here that, like, for example, O stands for OSPF, which means that this route has been learned throughout the OSPF routing protocol. C means directly connected here. S means static, and so on. Like, for example, our previous route, this is like directly connected network. 2.0. This is 12.0 directly connected. Now, the new entry that has been installed in the routing table of R2 is 192.168.1.0/24. B stands for BGP, which means that this route has been learned from BGP, and it's selected and it's been installed in the forwarding information base of the router. And also here you will see the next hop, like how do you reach this network? And as you will see here, the next hop is 192.168.12.1, which corresponds to R1. And this could be like seen on the topology here, because when we need to reach network 192.168.1.0, we have to use the next hop R1. And this is the interface that's corresponds to like the facing the network, the next hop. So if you show the the BGP table of router R2 here, show IP BGP. Again, this is the network that has been learned from R1 because R1 advertised this network. It's valid, and it's the best path that is used because there's only one path, so that's gonna be picked. The next hop to use it is the same 12.1, and these are the metrics. And as you see here, there's 100.I, and this corresponds to the AS path attribute. Means that in order to reach this network, you'll first go to autonomous system 100, which basically includes the network. However, if the BGP table on R1 didn't have this autonomous system because it was originated from there. Okay, now I've only advertised the network on R1. I will repeat the same process on router R2. So in R2, I will advertise the network directly connected to it, which is 2.0, and I will follow the same steps. This is router R2 terminal. I will enter the configure mode, configure terminal. I will enter the BGP configuration mode, router, BGP 200. And now I will advertise the network 192.168.2.0/24. And then I'll exit the BGP mode, configuration mode. Now I'm in the same terminal, router R2. I will show the BGP table of this router, and we'll see what are the modifications that happened after we advertise this network. So the command is show IPBGP, show IPBGP. So this network has already been advertised from R1. We already talked about it in our last step. Now this network that we just advertise here is also installed in the BGP table. So 192.168.2.0 is valid. It's the best path in BGP. The next hop is 0000 because, again, we advertise this network locally, and these are not set. The weight is the highest because it's originated from here, and the path is only I because, again, it's only advertised from this router itself. Similarly, I will show the routing table of R1. Now I'm in router R1. Show IP route And here, you will see this network 192.168.2.0 is installed. It's learned via BGP. The B stands for BGP. It's installed the best path. It's valid. And the next hop is 192.168.12.2, which corresponds to router R2, in particular to this interface that's directly connected to R1. Okay. Now, after configuring BGP neighborhood as well as advertising the networks, we will check the connectivity between host H1 and host H2. So I'll open host H1 terminal. I will launch a ping command. And here you will see a successful connectivity test between host H1 and H2 due to the BGP configuration that we configured on R1 and R2. Similarly, you can test it as well on host H2. Ping 192.168.1.10. And again, you will see a successful connectivity test. So with this, this concludes lab number 3, which again, configuring BGP neighborhood as well as advertising BGP networks. This is a very simple and BGP configuration between 2 autonomous systems. In our next hands-on session, we will cover more advanced BGP attribute, which is the local preference attribute as well as the MED attribute, and with a more complex topology. So with this, I will pause here for any questions or anything you want to ask.
Well, thank you, Ali. I don't see any question coming, but thank you for this presentation.
Thank you.
As Ali said, this is the basic configuration. Next session, the last session of the workshop, the hands-on session, we will talk about how to steer traffic, how to modify the path that are selected by BGP. And again, the other thing that I want to mention is that you have this lab available. Those will be available for the next 90 days, so 3 months. And there are, Ali, I don't know if you want to show the lab libraries, because we have a few minutes. We can show the more advanced lab libraries. The intro is what you're covering right now. So you covered this lab number 3 in your screen.
Yes.
Yeah. Then you will be covering, I believe, lab number 8 in the next hands-on session.
Yes.
And there is another library also underneath that, which is some additional advanced topics.
Yeah.
I think that those cover some attributes that were not covered in the previous library, which such as multi-protocol BGP. That's what I remember.
Yeah, that's correct. MPBGP.
Okay. I don't see any other question. There is one question here. Will the recording be available for later viewing? Scott, yes, we're recording and we will be posting again in YouTube, and also we will add a link in our workshop website. So this will be posted soon. Another question here, could we download the Mininet configuration files for testing with Mininet Home? The answer is yes, and actually the Ali is showing right now. There is a link to the virtual machine. That virtual machine, if you download and just run on your machine, it has everything that you need to run these lab libraries, including the lab manual. So you have everything you need in that virtual machine. Dave has a question. How do you find the advanced lab? Dave, if you just contact, and this is what you did right now, we can make them available to you. So Jose, could you just take note of these and make the advanced libraries? Actually, we can make available to all the registered users.
Sure.
Yeah, and we will be sending email with this information. All right, I think that those are all the comments and questions. So with that, what I will share my screen momentarily, Ali. So, and this is concluding our hands-on session number 3 of the workshop. So we will have a break for the next 30 minutes, and we'll be in the breakout rooms. There are 6 breakout rooms. Number 1 is persona, number 2 data mobility, number 3 SIMS DMC, 4 routing policies, 5 number 5 network security, and 6 programmable switches. Christy, I don't know if these rooms are already open.
They are ready. I'm going to pause the recording.
Okay, we're gonna start our last hands-on session of this conference workshop. So Ali will be presenting, going through this hands-on session number 4, local preference and met attribute. We're still talking about BGP. So Ali, do you want to start this session? Go from the enroll and then start the lab?
Yeah, sure. Do you want me first to start the presentation and then I'll do the enrollment for the hands-on session?
No, you can start the presentation. I will let you lead this as you prefer.
Okay. So I'll share my screen. Okay, so now we're in the hands-on session, local preference and the met attributes. You can find again the PowerPoint and the PDF here. This is the PowerPoint overview that I will be using for this hands-on session. And so I'll just go briefly an overview of the BGP attributes and how BGP selects the best path. And basically, there are multiple attributes that BGP uses to select the best path when there are multiple paths to the same destination. In this hands-on session, or in particular in this lab number 8 that we'll be covering, we will talk about the local preference attribute, as well, which is point 2, as well as the med attribute, which is point 6. But there are other BGP attributes. Some of them we also cover in other BGP labs. Essentially, without any advanced BGP configuration or without route manipulation, BGP selects the path which has the shortest autonomous system path attribute, which means it chooses the path that has the least number of AS autonomous system hops. However, if you're a network administrator and you want to route the traffic through a different path, you have some BGP attributes such as the local preference and the MED to influence incoming and outgoing traffic. So what is the local preference attribute? It basically indicates to routers what is the preferred way to exit this autonomous system. And the higher the local preference value, the better, or it has a higher precedence. So in this example, as we see on the right hand in this topology, we have network autonomous system 64520 that receives routing updates from 172.168.0.0 through two paths or two directions. The first one is through autonomous system 65500, which is only one hop away, one autonomous system away. And the second one is through two autonomous systems, 65000 and 65250. So again, without route manipulation, as I mentioned, the autonomous system will choose the path with the least number of autonomous systems, which means this one. However, you can configure the local preference within this network itself, so that this route or this direction has a higher precedence over this one. So in particular, you can configure the local preference on router RA, so that it has this path has a local preference 200, and this on router RB, this path has a local preference 150. So now the information will be advertised through all the routers, and this network will be selected to steer the traffic from AS autonomous system 64520 to this network. They will be sent out to router RA as an exit point from this network. So the local preference is intended to influence all outgoing traffic. But however, what if you want to influence incoming traffic to your autonomous system or to your network? In this case, you will use the MED attribute, which indicates to external neighbors what is the preferred path into autonomous system. So in this scenario, let's say that you are the network administrator of autonomous system 65500, and you want to influence all incoming traffic from this autonomous system AS65000 through the link connecting router A to B. You will need to configure the MED attribute within your autonomous system, in particular in a router RB and RC, so that the lower the MED attribute, the higher the precedence, which is in contrast to the local preference attribute. So in our case here, we configured the MED attribute on this link to be 150 and on the other link to be 200. So now all the traffic from network autonomous system AS65000 to 65500 will go through the link connecting A to B. And some use cases that you wanna why would you wanna change the like the path, incoming and outgoing traffic, is sometimes you could have like a higher bandwidth primary link, as we will see in our lab topology. So in this hands-on session, we will be covering lab number 8. This is the topology. You have two networks, two autonomous systems. The ISP has autonomous system 100 and the campus network has autonomous system 200. And as you see here, they're connected through a primary link and a secondary link. And our goal is to route all the traffic exchange between these two autonomous systems through the primary link. Unless this primary link fails, so that's when the secondary links come in handy. So to do that, we'll configure the local preference and the MED attributes. And this is just a brief configuration that I will go into details in the lab. For configuring the local preference attribute on R2 and R3, you will establish a route map, you will set the local preference, and you will attach it to a BGP neighbor. And similarly, you repeat the same local preference configuration on R3 with modifying the local preference value to be lower, because you need the primary link to be the one that will be used by default. Now, after you configure the local preference, we'll also check the BGP table of the routers, so that now R3 is, we will notice that R3 will no longer use this path, but rather it will use this path, which goes through the primary link. And similarly, now to influence all the incoming network traffic from the OSP, you will configure the MED attribute in a similar manner to the local preference attribute. And you will see how the OSP will be affected by the MED attribute, so that when it routes traffic to 192.168.3.0, it will choose the primary link rather than the secondary link. So we'll go over this in details in our hands-on session. Again, to get into the pod, you can click on the enroll here. You will see the set of BGP labs in case you've already enrolled into it. For me, because I'm already signed in, it will immediately show this. I'll go ahead and choose lab number 8. Just be aware, because there's lab number 8 and lab number 8.1. We're only focusing on lab number 8. So I will click to make a reservation. Just take a few seconds to initialize. Okay, so again, here's the content of the lab. I will go ahead and open it. Just split the screen into two. And on the right-hand side, I'll be using the pod. Again, this is will be proceeding the similar way as I was doing in the first hands-on session. Here you will see the overview, objective, lab settings, password is password. This is an introduction if you want more information about the BGP labs. And this is our topology. I'll be starting from section 2.2, which is opening a mini edit. Here, the password is password. Again, I will load the topology. It's already there. I will just load it. The topology of lab number 8. Click on File, Open, lab number 8. Select the end topology. And now I will load the IP addresses, because I don't want to configure them manually. So I'll just launch a script that will do that automatically. You'll need to open a Linux terminal, the right icon to the third icon to the right. Go to the directory, which is lab number 8. You will execute the command to load the IP addresses. And in this case, and I will exit because I no longer need the Linux terminal. Now, when the IP addresses are loaded, I can go ahead and click on the Run button here so that the emulation starts. Again, if you want to check the links of our topologies, you can just write here links, and you will be able to verify which every device to which interface is connected to which other interface, which other device. Now, similarly here, you can verify the IP addresses of the hosts, H1, H3, H2, so on. I'll just skip over that because the IP addresses are already configured. Can similarly verify the routing table of host H1, H2, and the default route of H1, H2, and H3. Now, moving to the routers, I will have to do this. Hold the right click on R1 and select the terminal. I will launch the Zebra daemon and enter the VTYSH session. Now I'm in the FRR shell. You can verify the routing table of R1 just to validate the IP addresses are already configured correctly using the script that we launched earlier. Similarly, this step is necessary for every router to enable the Zebra daemon. So I'll go ahead and do it right now. Zebra VTYSH show IP route just to validate. Similarly, on R3, hold the right click terminal, Zebra VTYSH show IP route. Now I've launched the Zebra daemon, validated the IP addresses. I'll move directly to the BGP configurations on the router. So we'll begin with router R1, and because R1 is in a different autonomous system than R2 and R3, then we'll be configuring EBGP. But it's it's the same configuration, just like a different terminology, EBGP and IBGP. So we'll go to router R1 here, click on it. I will exit to the Linux shell to enable the BGP daemon. And I will go ahead and go into the VTYSH session. Now I'm in FRR. Go to configure terminal. And now I'll be assigning the autonomous system number of router R1, which is 100. So to do that, you write the command router BGP 100. It's the same configuration as so far as we've done in the previous hands-on session. Similarly, we'll assign a router ID for R1, and we're following the same convention. BGP router ID 1111. We'll establish a BGP neighborhood first with router R2. Router 192.168.12.2 is this one. So now R1 is establishing BGP neighborhood with R2. Neighbor, specify the IP address 8.12.2 and the autonomous system of your BGP neighbor that you're peering with, which is 200. Refers to the campus network. Now, similarly, R1 is also connected to R3, so we need to establish a BGP neighborhood with R3. So the same command, different IP address, neighbor, IP address of this link, 192.168.13.2, and the autonomous system of the neighbor, which is also 200, because R2 and R3 are in the same autonomous system. Now, R1 will need to advertise its network so that R2 and R3 know about 192.168.1.0. So to do that, the command is network 192.168.1.0/24. Now I will exit the BGP configuration mode. And I will check the BGP table just to make sure that this network is advertised through BGP. So the show IP BGP. And here you'll see that the network 1.0 has been advertised. It's locally advertised. I just went over this fairly quickly because we already did the same steps in the previous hands-on session. And similarly, now we're configuring EBGP and IBGP on routers R2 and R3. And while we're EBGP is going to be between autonomous system 200 and 100, and IBGP is going to be between R2 and R3. So I will go to R2 terminal now to configure BGP. Before that, you need to enable its daemon. So you will go exit the Linux shell, BGPD to enable. That's step number 2. Go back to VTYSH session of entering FRR and configure terminal. Assign the BGP, or what is the autonomous system number of R2? It's 200, router BGP 200. Same. And assign a BGP router ID for R2. So it's BGP router 2.2.2.2. And similarly, I will be establishing a BGP neighborhood with R1 and as well as with R3. So first with router R1, the neighbor command, the IP address 192.168.12.1, which is this one, and the autonomous system number is 100, corresponds to R1. Similarly, the neighboring command for IBGP is the same. You also write neighbor 192.168.23.2, and the remote autonomous system is the same as the router R2, which is 200, because they're both in the same autonomous system. Now, step number 9, you will be advertising the network. And router R2, it will advertise the network 192.168.2.0, as well as the external network. So step number 9, you're advertising, R2 is advertising its internal network 192.168.2.0/24. And it will advertise network 192.168.12.0/30. And the reason why we're advertising this network, because R3 here does not know about the primary link over here, right? Because this is the primary link and this is the secondary link. So in order to for R3 to know to have an entry to the primary link in its routing table, you need to advertise it by router R2. So now we configure BGP on R2. We can exit the BGP configuration mode using the command and Similarly, we will repeat the same BGP configuration on R3, which establishing BGP neighborhood and advertising the networks. So I will go to router R3 here. We'll exit to the Linux shell. I will enable BGP daemon, BGPD. I will enter back to the VTBRSH session, which allows me to configure BGP. Configure terminal, router BGP 200, autonomous system of R3, and assigning a BGP router ID 3.3.3.3. Establishing a BGP neighborhood with first R1, which corresponds to 13.1. And one thing I didn't comment on is the IP addresses. The convention that we use is like 192.168.168 is fixed, and then the second one corresponds to the indices of the router. So for example, the link between R1 and R3 is 13, and then R1 has .1 and R3 has .2. Like the lower, it will take it incrementally. So this is the convention that we use in all our lab for simplicity. Now back to establishing a BGP neighborhood. Neighbor 192.168.13.1, remote autonomous system 100, this one. And the next neighbor is R2. So the IP address would be 192.168.23.1, a remote autonomous system 200. And R3 will advertise two networks. First, its internal network 192.168.3.0 here. And the second one is 192.168.13.0. So that R2 knows about this network, knows about this secondary link. If you didn't advertise this network here, the external one, like someone would say, why would you advertise external network? Otherwise, you would need like an IGP inside your like campus network, so that R2 knows about the secondary link and R3 knows about the primary link. And in fact, in lab number 8.01, we have, like, instead of advertising this network, we have an IGP like running, OSPF running within this network. So if you want to have a look at it. So back to advertising the network, the first network is 192.168.13.0/30. And the next network is 192.168.3.0/24. Okay, now that we have already configured BGP on R1, R2, and R3, I'll exit the BGP configuration mode on R3. Then I will check the BGP table. So show IP BGP, just to see what are the modifications that have happened so far. And as we see here, I think okay. Might have. So on R3, as we see here, there's the R1 is through 192.168.13.1, but the other one is not run. I think I maybe made a mistake here.
your neighbor statement was a type in there.
Oh, sorry. I will go ahead and just fix it. BGP 200 neighbor 192. I forgot the dot. 23.2 remote autonomous system 200. Okay, let's hope now it's working. Okay, perfect. Thank you. Okay, now after displaying the BGP table of R3, we will see here that router R3, in order, let's look into this entry, these two entries. So the network 192.168.1.0/24 has two paths. The first one is through the next hop 192.168.12.1, which is this one, through the primary link, and the second one is through 192.168.13.1, which is directly connected to R1. And to see which one BGP is using, we can look into the arrow sign, and here the arrow sign indicates that this is the best path. So the best path that is basically used to reach the network 192.168.13.1 .1.0 is the secondary link. And why is that? I just will go back a little bit to the BGP attributes that I mentioned. And so far we haven't configured any BGP attribute. And by default, if you see here number 7, the BGP prefers the external path over the internal path. So here, this path 192.168.1.0 has been advertised internally through 192.168.12.1. So the primary link is advertised by R2, and the secondary link is advertised externally by R1. So by default, R1 will choose this path. But as we mentioned, our goal is to configure BGP local preference so that R3 all the network traffic from the campus network will go through the primary link. So we will do that in the next step, which is focusing on the local preference attribute. And as you see here, the local preference haven't been changed. The path is 100i because you need one autonomous system to reach it, and same here, same as here. Now we need to configure the local preference, as you said. We'll go to router R2 first. Go back to configure terminal. And I will set a route map, which is basically route map is like a permit close, or you can say it's like an if else condition, allows like more programmability for the router. And I will use it to set a local preference for this route. So you write route map, and I will call it primary N because just like naming convention, primary N, and the permit, and you will assign a sequence number 10, which is the default sequence number. Next, within this route map, you will set the local preference attribute. So here in this lab, we set the local preference to 150, and that's for the primary link. So eventually, the secondary link should have a lower local preference value. So set local. I just click on the tab to auto-complete it, and we'll set it to 150. Now you can exit the route map configuration by writing exit. And you will go back to the BGP configuration so that you assign this route map to the neighbor. Now router BGP 200 to enter BGP configuration mode. And in this step here, what we're doing is we're attaching this route map, which is called primary end, that we have created here, to the neighbor R1. And we're doing that because we want to set the local preference attribute to attach it to this neighbor, or basically to this path. So we write neighbor 192.168.12.1 route map, and the name of the route map, which is primary N. And you write N because you're basically referring to like the influencing incoming traffic. Now I'll exit the BGP configuration mode. And I will repeat the same steps on R3 and set the local preference of this path to a lower value so that this is the primary and this is the secondary. So I'll go to router R3. First, configure terminal. And I'm following here the steps summarized in number 8, step number 8. Create a route map. I will call it secondary N. You can call it whatever you want. And permit 10. Again. Set the local preference. We're setting it to a lower value because we want it to be have a lower precedence. I'm setting it to 125. Now exit the route map configuration. Enter the BGP configuration, router BGP 200. And now the route map that you created here will be assigned to the neighbor R1 as follows. 13.1 is R1. Sorry. Route map, secondary N. Same configuration, and I'll exit. Now, to verify that, like let's see, now we've configured the local preference attribute. In order to verify that, let's check the BGP table of R3 and see if there are any changes. Show IP BGP. Okay. So now this entry here, 190, this network address 192.168.1.0. If you notice, the arrow here has moved from here to here, and this means that now, in order to reach this network, you will use the next hop 192.168.12.1, which is here, which is this network, this address. So now, if router R3 wants to send any traffic to this network 1.0, it will use the primary link. Again, the local preference here, you will see that now it is set to 150, and for the next hop, the primary link, and it's set to 125 for the secondary link. So all the network traffic now from R2 as well as R3, because R2 will by default use this primary link. R3, after configuring the local preference attribute, will use also the primary link. And we will also test that later on. Okay. Now we've achieved like the first goal of our lab, which is basically steering all the traffic from the campus network autonomous system 200 throughout the primary link. However, what if we want to also, like, what about the incoming traffic from the ISP or Autonomous System 100? Let's see what's happening here. So here, let's go to router R1. And you will show the routing the BGP table of R1. So let's see here what's happening. Basically, let's look more specifically onto this network, 192.168.3.0. Let's see what's happening. R1 here will use, in order to reach the network 192.168.3.0, it will use the next hop 13.2. And that's, you can see it from the arrow sign over here. So what we want to do is basically make R1 steer all the network traffic through the primary to 192.168.3.0 through the primary link rather than the secondary link. So we'll go back to R2 and configure the MED attribute. Configure terminal. It's similar to the local preference attribute, by the way. We'll create a route map. Route, this is for the MED attribute, primary MED. And you will assign a value for the MED attribute. And here, in contrast to local preference, the higher the value, it's the better. So here will be set to 50. You will exit the route map configuration. And now we'll go back and assign it to the neighbor. So neighbor 192.168.12.1 is R1, route map primary MED out. So this is the route map that we created, and this is out is to refer to all the outgoing traffic. So we'll hit the enter. Now the route map is assigned to our neighbor. Similarly, I'll repeat the same process on R3 to see what are the and see what are the changes. Now, again, configure terminal, route map, secondary, permit 10, and because, as we said, the MED attribute, the lower the better. So in this case, on R3, it needs to set the local the MED attribute to a higher value. Here we'll set it to 75. And we'll hit exit. Now, after initializing the route map, I'll also assign it. And let's attach it to our neighbor, 192.168.13.1 route map, secondary out. So with that, I've configured the med attribute on router R3, and on router R2 we assign it to 50, so that this link has a med attribute 50. On router R3 we assign it to 75, and as we discussed before, the med attribute will influence all like external autonomous system. So even though we, like, let's say if we are a network administrator in campus 1, we don't have to have access to autonomous system 200 or the ISP in order to steer the network incoming traffic to our autonomous system, but rather from the network itself, we can do that throughout the med attribute. So that's why we didn't configure anything on R1, and we only used R2 and R3. So I'll just pause for a few seconds if anyone has any question or comment on the local preference or the med attribute so far. Okay, it seems that there are no any question or comment. Okay, now after configuring the med attribute, I'll go ahead and verify that it's now working. So how do I validate that? I go to router R1 and I make sure that R1, when it steers the traffic to 192.168.3.0, it will take the primary route, which is through R2, rather than the secondary route, which is through R3. So I'll go to R1. Let's show the BGP table. And here, you will see now that, where is the network? Okay, here it is. You'll see that the network 192.168.3.0 will have the next hop as a preferred one, 12.2, which is this router. And you see here the meta attribute is 50 for R2 and 75 for R3. So now all the traffic from this network ISP 1.0 to 3.0 will go to the primary link. And we will also validate that through another method. I think there's a question here. There's the entire router. Does the entire router need to be assigned to an autonomous system, or you can specify the interface? In our configuration, we are assigning the whole router for an autonomous system. But I believe if you have multiple routing tables, which is through VRF, then you can assign it to a specific interface. But we're not doing that in this lab series. I can check that here real quick. Router BGP. You can see here there's a VRF option where you can assign to which VRF table that you wanna in case you're using VRF. Anytime. Okay, so now we'll do the last test just to verify that our configuration is working, and now the traffic incoming and outgoing from AS100 to AS200 is only through the primary link. I will go to R3 and I will perform a trace route. So we'll just end. So the trace route command enable you to see what are the hops that the packet is going through. Specify the source 192.168.3.1, which corresponds to this network, and where's the destination 192.168.1.10. And here, as you see, the route or the path that the packet takes from this network 3.0 to 1.0 is first through 23.1, which is this hop, and then 12.1, which is R1, this interface, and then reaching to the destination, which is 192.168.1.10. So now with the trace route command, as well as the route, BGP and table, we've verified that our configuration is working. We verified that using these two commands, we can steer the network traffic as we wish in the network. But the last thing that I want to comment on is, what if the primary link fails? So will the secondary link come in handy? And that's what we'll try. So we'll go to R1. And I will shut down the interface R1 ETH1, which is the primary connected to their primary link. So I'm just like emulating that the primary link is down. So interface R1 ETH1. And the command to shut it down is shut down. Let's see how the traffic is now steered. And just check the BGP table again one more time. And here, you will see that the two networks now, 192.168.2.0 and 3.0, they will only have the next hop 13.2, which corresponds to the secondary link. And that's expected because we have shut down the primary link, or basically emulated that it's down. So we'll also do a trace route test. Same, I'm still in R1, exit to the Linux shell. Trace route. And as you see here, in order to go to even this network here, H2, there's no way that you will be using the primary link. However, you will be using the secondary link 13.2. And then from 13.2, you will be able, it will forward it to R2 and then to the final destination, which is 2.10. So with that, we conclude our lab. To sum up, we learned how to we learned about the local preference attribute that basically influences all the outgoing traffic within the autonomous system. And the local preference attribute, one thing I haven't mentioned, is not advertised to external autonomous system. So it's only advertised within the IBGP neighbors. And that's how R2 knew that this is the primary and this is the secondary, and similar for R3. We also tested that using showing the BGP tables. Moving forward, we configured the MED attribute so that now all incoming traffic from external autonomous system will follow the primary link as well, rather than the secondary link. And the difference between MED and the local preference, like this one difference, is that the MED is shared with external autonomous system, like one hop away. So that's how it allows us to influence other external autonomous system that we don't have like direct administration on. And finally, we have tested that throughout traceroute command, and we saw that how a primary and secondary link could be useful, just in case the primary is down, so the secondary will be used instead. So with that, I conclude my lab and configuration, and we'll see if there's any question or comment.
Well, thank you very much, Ali, for this. I don't see any question, or some questions were already clarified in the chat window. So we're a few minutes early. I want to remind you, this is available, and we're just covering a little bit of the labs that are available. There are also some exercises, as Ali said at the beginning, exercises that are somehow the use case. I remember one use case that Brina was mentioning, following the longest autonomous system path. So how do we steer traffic? Exactly what Ali was showing here. Thank you very much, Brian. Well, I don't see any questions. So actually there's one, Ali, if you want to read that, or you want me to read and want to address that?
With FRR, is there a way to configure BGP with just a config file alone instead of the CLI? Yes, it is available, and I can show you that here. So with FRR and like our topology, if you're using our virtual machine, I think there's this file right here. Here you will see there are, because like we have up to like 30 routers, and our labs, we don't use this much of routers, but for every router there is a directory where you will see the configuration. So like let's BGP, the configuration is basically here, and it's empty now because we haven't saved the configuration. So one thing you can do after, like let's say you have configured everything and you wanna save your configuration, you can enter the VTOSH session and you can like write here. So now, because we have we only use BGP and Zebra for the interfaces. So if I click on it again, you will see that the configuration now is committed to the conf file. And similarly, you can use this file to do whatever you want. If that's answer your question. Does FRR have a commit mode? You mean like as in write? As in Juniper?
The answer is I'm not aware, or we don't use commit. Everything that you configure go to the configuration file immediately. Doesn't have the commit. Now, if you want to save in, it's somehow similar to the Cisco router. When you do a change of configuration in a Cisco device, you are writing in the running configuration file. This is what Ali is showing. It's just directly writing in the configuration file. It's gonna take, yeah.
Some Cisco, and I don't know if Zebra or FRR does this, but you know, on a real Cisco router, you can do a write, commit, confirm kind of thing, where and specify a time period. So if you really botch the config in 3 to 5 or whatever minutes you set, it'll revert to the old config again. So that's available. Kind of like that would be like Juniper's commit confirm.
Yeah, and we don't, at least we never use FRR, the one that we're using. I don't see this feature. The question from Steve, how were the tools FRR, Zebra, and BGP daemon chosen as opposed to other BGP router tools? When we decided to do this lab library, we were looking for open source that were somehow known by the open source community, and we just found FRR to be quite fit quite well for our project. Perhaps there are others that we might explore, but we just found this to be somehow popular into the open source community. And Steve, by the way, FRR include other protocols. You are mentioning BGPD, which is the daemon for BGP, but it has, when you install FRR includes OSPF, READ, static routing. So it includes a whole set of protocols already. Okay, any other questions? Well, Ali, thank you very much for this presentation. Again, this library is available for 3 months, and we can extend and we can make available. Some of you already requested access to other libraries like Advanced BGP. Just let us know if you want to access those, and we will make them available to you. And with that, we will start the last session presentation of the workshop. I would let Jason to take from here.
Thanks, Jorge. As Jorge notes, this is the last talk of this workshop. We do want to extend our gratitude to everybody for tuning in and asking thoughtful questions over the past 2 days that we've been holding this. I think it's been really good to see people thinking critically about some of these topics. And along those lines, we did want to feature a little bit of a talk on BGP and routing security. Even though we're not going to do any hands-on sessions to this, it's a little bit of a prelude to some of the work that EPOC and others are participating in. So with that, I'd like to introduce Hans Adelman, who's going to be giving this talk today. Hans is from Indiana University International Networks, where he's the network architect and also a key member of the EPOC team, which is joint work with the ESNet. Hans has had a long career in networking, joined the IU Global NOC in the early 2000s, and has done a lot with networking and routing, open flow based networking, network security, technical training, list goes on and on. Along with that, he's also the SC23 SciNet chair, so he may roll a little bit of that information in near the end of his talk, as we are actively always seeking volunteers to participate with SciNet. So I will throw it over to Hans to lead us through a little bit of a discussion on routing and network security. And
Thanks,
then
Jason.
after that, we will go into a little bit of a Q&A before we end for the day. So take it away, Hans.
And if I don't talk about SC and SciNet at the end, remind me, because that's a good bump. So today's been pretty great. We've done a lot of BGP basic stuff. We've learned a lot of interesting things. I wanted to end the day and kind of scare everybody. Maybe not really scare, but BGP, and real quick, just a quick agenda for you later if you want to go through it. BGP, Brenna said earlier in the day, it does make the internet work. There are 74,000 autonomous systems or different networks out there. Over 1 million advertised IPv4 routes, almost 200,000 V6 routes, and more added every day. Without BGP, none of these networks would talk to each other. And because of that, BGP is a really big attack vector for people, right? There's a lot of different things people could do if they can assault BGP, or even maybe it's not a malicious attack, maybe it's just a human error or misconfiguration. No matter what, we can cause real damage to the entire internet with very few keystrokes. So, and each router, I say here, running BGP builds its own routing table with best path information to whatever subset of the internet it can get to. Hopefully your computer or whatever computer you're on somehow can get to almost anything that's currently active on the internet. Thinking about that, that kind of blows my mind, right? It's big. And what's even a little scarier is BGP is a fairly old protocol, right? It's been in use since 1994. You can go and read the RFC if you'd like. And back then, security was not a concern. Ugh, oh, excuse me. The trees are trying to kill me. So I've taken some Claritin and some other things to help, and it's unfortunately left me a little tired. Anyways, BGP is old. There was no security baked in. If another router advertises and says, hey, I can get you to this address, your BGP by default will believe that and send traffic to that guy, whether it's truth or maybe a bad actor. And then your BGP instance can also, by default, possibly re-advertise that bad or good information to other peers, depending on where you sit in the network world. So there are three pretty big things that happen, and have happened for years now. Hijacking, leaking, spoofing, and we'll get into each one of these. And I'll talk about what Manners is in a little bit. However, just in 2018, they recorded over 10,000 routing outages or attacks or misconfigurations. So, these are ongoing. And, as I say, there 40% of all of these incidents are believed to be attacks. And, like I said at the beginning, one small misconfiguration on your campus's BGP instance could possibly scale to become global problems. Personally, myself, I've done this. I've brought, on a certain internet provider that I used to work for, I once brought most of the network traffic from all over the country to Cleveland and then promptly black holed it. That was a learning experience for me, and it was just a misconfiguration. So that was fun. It lasted about 10 minutes, and I thought my heart was going to stop. So route prefix hijacking. When a network advertises or originates a route that belongs to another network without their permission. Like I said, not always malicious, right? You could have an IP address that's awful close to another person's IP address, and maybe you just misconfigure it. And there, I've, through the entire slide deck, I've put a lot of references. Feel free to grab the slide deck. I believe Jorge's already posted it, and take a look at some of that. There's deep dives for each one of these slides, or most of the slides. So hijacking, how it works, right? So, you learned how to advertise your prefixes earlier today. And so your legal advertisement down here, AS1, he says, hey, I have this /22 I'd like to advertise out, and it's going out. And as we talked about earlier, the AS path is additive. And so you get up to AS4 and he says, oh, I know how to get there. I go 3, 2, 1. Well, except let's say there's an illegal announcement, whether it's a hacker or just a misconfiguration. He advertises that same IP address, that same /22, and it gets to AS4, and hey, look at that. That's a shorter AS path, and we learned that by default, BGP will go for that shorter AS path, and we learned why that may not be right for R&E networks anymore. But in this example, he said, oh, hey, I'm going to go this way. And so all traffic destined to that /22 from this AS goes right to AS5 instead of AS1. Now, whether that's malicious and he's sniffing that traffic, or just possibly even a campus network that had a misconfiguration, sucked in a bunch of extra traffic, and maybe AS5 is now, oh my goodness, I'm in trouble too, because it's, may have overwhelmed its pipes with all this added traffic coming to it that it wasn't expecting. Maybe here, a more specific prefix. So the hacker, instead of getting it via AS path, he puts a /23, which is a more specific prefix than a 22. So over here in the RIB, the routing information table of AS4, he says, oh, I have, I can go to AS20 or the 20/23 or the/22, and I'm going to send my traffic to AS5 for that /23. So an interesting example, and this was back in 2008, but it was pretty crazy because it affected YouTube and Google. This is a very large one. So over time, Google, this is one of their, YouTube, this is one of their major IP ranges, the /22. And sometime on Sunday, the 24th, AS 17557 starts to announce a /24, which is a subset and a more specific subset, like we just talked about, of that /22. Routers around the world receive that announcement, and a whole bunch of YouTube traffic is then directed to Pakistan. YouTube at this point, about an hour, little over an hour later, notices something's going on, starts announcing 2 /24s to try to get around that, and be more specific than the illegal advertisement. And they do get some traffic back. At that point, 10 minutes later, they realize, oh, that's not specific enough. Let's get a little more specific. And as routers around the world grab those advertisements, things start going slowly back to normal. And then, of course, PCCW noticed there was a problem, made the AS path longer towards Pakistan, and that also helped traffic go to YouTube. And then, of course, another hour later, or about 45 minutes later, Pakistan realizes the problem and stops that hijack. And here's where the different case studies. This is a really interesting thing that happened. This wasn't actually really an attack. This was political in nature, I believe, where Pakistan wanted to limit some YouTube, and they tried to do that in their country with some BGP manipulation, and unfortunately caused a worldwide issue. There's a lot more, like I said, in the RIPE and the CNET articles there. Other hijacking examples, the 2018 one of Amazon DNS was interesting. That was actually malicious. They were looking at getting not PayPal, but some kind. They were grabbing payment stuff. So there was actually they'd hijacked these routes and were taking payment information into their network. And I assume at that point, looking at that payment information and doing nefarious things with it. 2020, Rostelcom hijacks internet traffic for Google, AWS, Cloudflare, and many others. This lasted only for a few minutes, but it was a pretty big. And they think, this one they think was a hijack, but we can't be sure. It may have just been a misconfiguration. So how do we fix these hijackings, right? We've talked about, we see this is a pretty big issue. We know there's hundreds of attacks a year, thousands of attacks a year. Well, RPKI, Resource Public Key Infrastructure, comes to the rescue. So there are regional internet registries, and these are the people that assign IP addresses to AS numbers. So if you come and say, hey, I want to get on the internet, you talk to one of these RIRs, and they say, okay, well, here's your AS number. Here's an IP address range that you can have. You're allowed to use these. And then, in the past, before RPKI or anything like that, we just trusted everybody and said, okay, that's mine, thanks, I'm going to advertise it. So now there's a few things that you can do. So with certificates and things like that, you can do route origin authorization that show, and that other people can check via RPKI to make sure that you're actually authorized to advertise that IP address. Allows you to verify addresses advertised to you from other people. This is just starting, well, not just starting, it's been around for a few years. You can see a nice little overview of RPKI there from Noction. But basically with this system, you can take a look at an incoming route and tell your router, hey, that's a valid, invalid, or unknown. And create route policy depending on those results, right? So valid, of course, you're probably going to want to accept. Invalid or unknown, invalid, maybe you want to just dump on the floor. Unknown, that's up to you what you want to do with that. I would really recommend is you bring up RPKI, don't do anything with route policy yet. just start looking at them and grabbing in your logs what it may be, right? So don't do valid or invalid for a while. Play with it, test it, put it in a test mode where you can see what your validator thinks it's doing and what your router thinks it's getting before actually going production with that. But anyways, you know, it allows you to not only reject on wrong AS, wrong prefix, but also to fix like the more specific thing that we saw earlier. You can do that as well. So inside that route origin authorization, we'll actually say, you know, Hans Adelman is AS number 15. He's allowed to do this prefix up to a /25. If you see anything more specific than a /25, that's probably not Hans. So looking at a different thing, a route leak, this is a different kind of attack or misconfiguration. And there's an RFC that describes this as well. And luckily for everything here, there is a lot of great tutorials, best operational practices, and RFCs that can help mitigate most of this. So a route leak is the propagation of routing announcements beyond their intended scope. In a campus case, if you were, say, multi-homed, or a campus or a stub network, as they're sometimes called, if you were multi-home, meaning like you had Verizon as one of your transit providers and say AT&T as another transit provider, you would take in, and actually I think I should, yeah. So you would take in, say, AS2's prefixes and re-advertise them to AS1, right? And if you're if you're like connected to a couple of tier 1s or even tier 2 service providers, when you do that, and if there's nothing, no validation or anything here, and AS1 accepts you as the best path to all the networks behind AS2, your pipes are going to get clogged very, very fast, right? So it's a good idea, not, you know, and I think I say this on the next slide. Oh, that's an example. Anyways, that's what a route leak looks like, right? So you're leaking someone else's routes out another of your network connections that you should not be originating. So this one's interesting. In 2017, as an example, Rostelcom again, they had a route leak that, and much like the Amazon DNS one, targeted e-commerce services, but instead of grabbing traffic and kind of black holing it and looking at it, what they did was a little more insidious. They took that traffic, took it into their network, and then passed it along, right? So every one of these e-commerce transactions that went from A to B went through their network, and they were able, you know, to grab that possibly and leave it to the side for later inspection or stealing of information, whatever might have happened there. Now, of course, this could have been a misconfiguration, like I've said, but it's just a pretty good example of what can happen with a route leak and how dangerous that can be. It can be more than just filling up your campus's pipes, right? It can be actually malicious. So route policy to fix leaks. There's a really great BGP operations and security RFC written to do just this, with a good primer there as well for best practices. The simplest thing is to not only originate what you have authority to originate, right? Don't originate anyone else's prefix without authorization. And I say that, so here's a couple of different things from the BCP. Loose inbound filtering, you know, not only don't advertise prefixes you don't own, but don't accept your own prefixes from another peer, right? That's probably bad. Filtering bogons, which are addresses not assigned. IPv4, as I say, not so much anymore, because I believe we are completely exhausted and all IPv4 space has been assigned. But there is a massive amount of empty IPv6 space out there. And there are bogon lists out there that you can just crawl and programmatically put into your route policy. Be careful of more specifics. I know, and this is a little weird in the R&E world, I know that a number of us do accept more than a /24 or a /48 for B6, but it's just something to be thoughtful about as you're writing your route policy. And then, of course, you can use strict filtering using things like RADDB and other places where people will actually put up their routing their prefixes and their routes. You can actually use scripts and tools to validate that kind of thing against the route registries. And that's all covered in the Operations and Security RFC. I really recommend taking a read of that. Outbound, like I said, only originate what you can, or only advertise what you originate. Don't advertise private space. We do see quite a bit of that. And I'll show you where you can see things like that happening. That's RFC 1918. So, you know, your 192, 168, your 10.0s, whatever. Don't just write a little bit of route policy to not advertise those. And don't advertise your management networks, your internal networks, things like that. And do not advertise the default route. That'll cause you to leak real bad. IP spoofing. This is mainly used in DDoS attacks. An attacker, you know, can create and send an IP packet with a false source address. This is, you know, very commonly used in DNS, Memcached, NTP. There's just so many different things that are vulnerable to this kind of things. And this was interesting. Just last November, Microsoft published this blog that they detected and mitigated a 3.47 terabits per second, 340 million packet per second, 15-minute long DDoS attack using UDP reflection. So, I mean, they claim, whoops, that this is the biggest attack that anyone has ever seen, and that is that. I mean, look at that. That's a pretty massive attack. They don't say who were the attackers, of course, but it's definitely worth checking out that blog and doing your best to mitigate IP spoofing, and that'll get you on the way to helping mitigate DDoSes on your network. It won't fully help you, but you know, it gets you some way there. And in this, URPF is really important. Universal reverse path forwarding. The router will actually check its forwarding information base for a source address in each packet. And if the router can't get to itself, like if it can't find that prefix that it's about to send out on the network or to someone else, in its forwarding table, it will just drop that packet because that's most likely spoofed. Can be done with ACLs as well. That can require some manual configuration. And amazingly enough, there's a wonderful RFC, and even better than the RFC, there's this BCP 38 that directly addresses how to fix or how to best mitigate spoofing and DDoSes on your network. This is a really great page. Both of those are really great. So like I said, you know, this all might seem very scary, but it's not terrible, right? There are ways to mitigate most of this. BGP sec, we're not there yet, but I thought it was worth mentioning. You can go and read the RFCs. There are a few open source projects doing this now, but no major router supporting this yet. So an RPKI will validate that NAS is allowed to source a prefix, to advertise a prefix, but it does not validate the entire path. So there could be attackers injecting things along the way into an AS path to change routing. BGP sec is here to help solve that. We hope that ITF is working on this right now. So hopefully soon we'll see something that will help you verify the entire path and kind of get rid of the man in the middle BGP attacks that we could be seeing. And of course, you know, we talked about this. Someone mentioned this a little bit earlier, asking about BGP communities and how secure they are. BGP, you know, forever, or for quite a while now, you've been able to configure a password and MD5 hash your packets, you know, between the BGP peers. It's a good idea. Unfortunately, make sure you have those passwords written down somewhere that all of your after hours engineers can get to, because you know, if something untoward happens in the middle of the night, you don't have that password written down somewhere, and he may need to bring up a new peering with that peer. It can cause problems. But yeah, so that helps secure the BGP peers talking to each other directly. That does not help for multi-hop BGP peers, and neither does GTSM, but it helps a little bit. So GTSM is interesting. It sets the time to live of BGP packets to 255 because most of the time our BGP peers are connected directly. That TTL should never drop. So if the router sees that the TTL on that packet is less than 255, it will just drop it and say, no, I'm not going to bring up BGP with that. So I've talked about, there's a bunch of different ways, BCPs, RFCs and stuff to help fix all this, but also there's this group now, the Mutually Agreed Norms for Routing Security, or MANRS. I really highly suggest you check out their website. Their goal is to improve the security and reliability of the global internet routing system. And they have programs, training tutorials, best practices, everything you would need to put the best security practices in place for your routed and BGP external infrastructure. Not only for campus and network operators, sub network operators, exchange point operators, even CDNs. So they have programs for everybody. These guys, and I really like their training programs. I've gone through a few of them and they are really handy. They're very easy, very well written. So it's easy to learn quickly some of these best practices. I just wanted to show a few things. You can join MANRS and say, hey, I am a MANRS compliant network. And as a campus or network operator, an end network operator, these are the things they asked for you, right? They would like you to do filtering. They'd like you to do that anti-spoofing. They'd like you to be part of the coordination effort and global validation. So, whether you're publishing your data on an IRR or using RPKI, things like that. You can read a lot more about them at their website and a few other places. And like I said, their tutorials are amazing. They're right, there's a link to them right there. And I know Brenna talked about this earlier, International Working Group. We're not exactly focused on security, but we would love to talk to you about security if you have questions. This is truly an international team of, I think, almost 150 members now. We have a fairly active Slack, a fairly active mailing list, talking about all sorts of different things. And I know Brenna went through, we're actually working on cases to improve performance, but we're happy to talk to you about not only the engineering focus, but also policy focus. Do you have questions about security policy for BGP or routing, things like that? We are happy to talk about that and help you, direct you in the right direction. So there's how you can join our routing group. I know we threw Brenna's name in the chat earlier. And these are some of those interesting, I just want to put this here, interesting routing and BGP resources. And I really enjoy route views. Route views is amazing. You can see routing tables over the years, daily or better than daily snapshots, going back years for lots of different networks that participate in route views. But you can also log into the route views. I think it's Quagga, one of their route views router, let's say, and actually get a live view of what they see of the routing tables of the world, right? So if you're bringing something new up in BGP and you want to see what the outside world thinks of what you're advertising, route views can help you with that. Twitter.com, the BGP stream Twitter handle is really great. It's a live stream of attacks, hijacks, and everything, and people, misconfiguring attacks, whatever. It's really fun, quote unquote, Twitter follower. And BGP stuff is just super interesting. You can see all kinds of stuff. It's like route views, not as connected as route views, but it has some interesting graphical views that I really enjoy. And then a couple other, you can see how the BGP tables are doing as well. A daily snapshot, he'll say, oh, I've seen this many prefixes on V4 and this many prefixes on V6, and this changed that much from the last time I saw them. So there's some interesting resources there I thought I'd point out. And, real quick, EPOC, we are NSF funded. We're here to make researchers' data transfers go faster. We're here basically to answer any networking question you have. And if we can't solve that question or help you with that question, we will direct you to the right people that can. And just like the Ghostbusters, we are ready to believe you. Check us out, and thanks.
All right, thanks so much, Hans, for giving that great overview. It looks like there were a couple of questions that did come in during the chat. I'll see if I can go up here to the last one that wasn't answered. Brian had asked some questions, but thanks to Adair for answering some of those. Does manners require BGP passwords?
I don't believe they actually do, but I would leave that to one of the manners ambassadors. If you're interested in manners and you want to talk to someone, I can get you in touch with Steve Wallace. He's at IU and also a manners ambassador. So I'd be happy to get you in touch with him.
On the subject of BGP passwords, I in a previous position at a MSO and ISP, I designed internet circuits that used BGP, and after a period of time, we started requiring MD5 BGP passwords, and I followed along with that, and I thought I could see a reason why, but I really couldn't ever. I never really got a great explanation of what exactly the benefit of that is, because with at least with the way that I've always seen and set up BGP, from the provider side, we always at the University of Nebraska and previously, we've always set up filters to only accept advertisements that we expect from the member, from the customer, that they get this 20
Sure.
and this 25 or whatnot, So I guess I don't really understand the benefit to the internet or the benefit to the network of requiring a password.
Well, as a network operator for many years myself, I agree with you. And honestly, I would almost say that I've had more issues with BB, and that's why I said always have that password written down from personal experience. I've seen that password bite me more often than once. I think in a lot of ways, they're in a multi-hop environment. I think it makes a lot of sense for man in the middle possible kind of things. Since without that MD5 overlay, your BGP updates are just zipping along in clear text. Now, if you're not multi-hopped and right next to each other, maybe that's okay. But with my networking security hat on, I could say, well, you're directly connected, but maybe there's an exchange operator switch in the middle, and maybe some bad actor were to get a hold of that, get a hold of some data on that switch between you two or something, or be able to see traffic from the switch between you two. With that password, you could stop that leak there. And now, granted, that is a corner case, let's call it. But
so I guess my understanding of setting up an encrypted password, that just password protects the BGP establishment. Is that right? Or is it also encrypting
no.
other types of traffic or other types of communication?
So the way I've read it is that it encrypts every update that goes out. So it's, I could be wrong, but that's the way I've always read it.
Okay.
So if someone can verify that one way or the other, or I can go back and do some more research and happy to hit you up offline. But the way I've understood it is that it hashes everything that goes out.
So even like route updates.
Yes, that's
Okay.
the way I always understood it. So I could be terribly wrong, but that's the way I understood it.
Okay, thank you.
No, thank you.
And one thing to note here is that Bill put in the chat room that they've had 0 outages from attempted BGP hijacks, but multiple outages from forgotten passwords during maintenance. So,
Which is, yes, which Bill is 100% right. And like I said, as a network operator, I have had that exact same problem. But it was network security talk, BGP talk. I wanted to just make sure that was out there and understood. So I can definitely be swayed either direction.
okay. And next question that has not been answered yet. It seems like some of the IGPs have implemented security pretty well. Is BGP sec using other routing protocol security implementations as a model?
I don't know, honestly. I've not, there have been many times I've wanted to join ITF working groups, and I just realized how much time I don't have to do that, unfortunately. So there is a lot of the RFCs out there. You're welcome. Then I bet you that if it doesn't explain it in the RFC, I'm sure someone that is listed in that RFC would love to talk to people about it. And actually, that might be something Brenna and I can get. We could get someone from the BGP sec teams to come give a talk to the routing working group soon. That would be really interesting.
Yep. Okay, well, that was all the questions that we had in the chat.
I see Michael
just
has
as
his hand. Michael has his hands up.
Sure, go
Yeah,
ahead and.
I did. I actually was just going to make a very quick comment just related to the passwords. For anybody who doesn't already know me on here, I run both the network at AMNH and I'm the CISO. And so anybody that does know me know I fight with myself often based on the network operator on me, and I got my start as an ISP, and then the data security side of it. And I have been with, and specifically with Bill, because of a misconfigured password, had a BGP go down on more than one occasion. That being said, from the network security point of view, and from our ability to do compliance and things like that, I think the main edge case is that we don't always know if we're directly connected to the peers or not. And that's
correct.
part of the question that we have to answer, and part of the risk that we have to deal with for our institution, because there is a tremendous amount of trust within BGP, but there's also a tremendous cloud. Everything is a cloud when you leave your own network. And so it becomes an issue of that little bit of extra, yes, a pain in the butt from the network operator. And believe me, I've wanted to rip more BGP passwords out just because they're a pain in the butt. But from our side of compliance and being able to sell the security and things like that, that is in part the reason why they're there. It gives us a level of trust that we would not have otherwise. And
For sure.
Your mileage may vary. I can be swayed probably more easily than some of my other CISO friends. But once you're kind of out connected to something that you can't verify what's on the other side of that line, those little extra help, little extra jumps give a level of comfort there. So it's
Michael,
but I would still do it.
You're talking about like a scenario not where like somebody is trying to connect on a different IP address or anything like that. You're talking about somebody spoofing that what you hope is your next hop, and then injecting different routes or
potentially. And I mean, again, it's a very edge casey kind of a thing. And I think the real issue here, and by the way, I do agree that MD5 is not useful as a hash algorithm anymore. But it's just like one other little step. So yes, it probably should be upgraded. But I just saw that comment. But I think the issue is just this actually came up to a certain extent in another conversation where people are now looking at all the different attacks that are hitting parts of the supply chain, things that we never thought about getting hit before are now getting injected in there. So I think it's the not knowing, it's the level of trust that we're trying to establish. So it may seem like an unnecessary thing. And like I said, I'm kind of dubious about whether or not it really impacts it. I'm also just saying, in terms of dealing with your CISO, who may not understand the networking on the same side of this, you may not win the fight of not putting them on there. And so I make it a habit of trying to put them on there. I know not every customer does. I know not every, provider does. In fact, I've had two of my providers, not NYSERNET, like actively say, well, we really don't normally put them on there. And we've still forced the issue. So once they're on there correctly, and if you use a decent way of maintaining that password, it's not that big of a deal.
Yeah, it's funny that you say some of the things you just said. In the network security breakout, Nathaniel Mendoza, the CISO of TAC, was talking about just how how much not only is he having, to convince C-level people, but convincing lawyers and insurance people now is huge. And then trying to, explain passwords and all this. And we're talking about maybe we do need to come up with a small working group that helps explain some of these more esoteric networking things in lawyer speak almost. if
Yeah, and
possible.
I would agree with that 1001%. And I don't want to make this go on anymore in case people want to leave early. But the biggest challenge that I believe a lot of technologists have between the CISO suite and the, say, more traditional networking suites, and then with other C levels and the compliance requirements and all the other things that we have to maintain, is understanding and being able to explain the risk and the reward on those. So if we're looking at it from a purely technical point of view, we can say, okay, this is somewhat dubious. However, our cyber insurance companies, our government contracts, our regulations that we have are expecting it. And so the CISO at that point says, okay, even if you could convince me, let's put it this way, you could convince me very easily right now as somebody who's run a network for years to dispense with this, to dispense with the MD5 passwords on BGP. There is going to be a checkbox someplace, somewhere, that if an auditor hits it, we're in bigger trouble. And I think that's if there's a security feature that we can leverage, that it isn't costing more, that we can put in there, that is what our cyber insurance carriers or our attorneys, or in an incident, every little ding that we would get potentially, even if it's a minor thing and it's not directly associated with whatever the incident is. These are all little things that kind of build up this wall here, and that's what the CISO is up against. They're constantly fighting what they don't know. So that's just a little perspective from the other side of this, from the left side of my brain versus the right side. And if I sound like I'm confused, it's because I've got both of them arguing in my head right now. But I'm trying to give the perspective from the other side.
So
I would
What we're up
very
against.
much appreciate.
Michael, I'm glad that you brought up the point about cybersecurity insurance. Are you aware of any companies that have policies out there that require BGP passwords? Has that ever come up?
Not that particular line, and just having, frankly, just redone all of our paperwork for our renewal.
Yeah.
Just literally a week ago. No, they're not specifically getting into that. What they are putting out there is, are you maintaining XYZ best practice here, best practice there? So if a best practice document along the way says, use an MD5 password on your BGP, and then you're not, it begins to make a case for your auditors, your cyber insurance, your incident responders, whatever it is, of what else are they not doing? It's that little corner of the wallpaper they start grabbing at. And that's ultimately what it comes down to. No, I don't believe the cyber insurance companies are getting that detailed, but it is a question of best practices here. Are you securing all these areas on your network? I will tell you that from 5 years ago, the documentation that we had to provide for our cyber insurance versus the documentation that I'm providing now is many times more expansive now than it was just a couple of years ago. And it just almost doubled the amount that I had to do over the last year, just with all the hacks that have come up. So it's just a question of not risk elimination, it's a question of risk reduction. And in the minds of the people with the money and the cyber insurance companies, that's what they're going for.
Thanks.
Really appreciate that, Michael. Thanks.
All right. Looking back in the chat room, it looks like most of the other questions were answered. Does anybody have any others related to this topic? If not, we can move towards sort of the final phase of the workshop here, where we just open it up for any other general questions. Looks like there's one, Hans, if you want to read it out.
Oh, Kathy, thank you. So no, we didn't talk about SINET stuff, and I'll spend 5 minutes here real quick. So supercomputing, the supercomputing conference, SC22, is coming up here in November. The conference itself is in November, and then again, of course, in 2023. 2022 SciNet is chaired by Matthew Zakauskas from Internet 2. 2023 SciNet is chaired by yours truly. And we are always looking for volunteers of all levels. So SciNet is a group of about 100-ish, sometimes more, network engineers, systems engineers, DevOps folks, and campus people, switches, Wi-Fi. Basically, what SciNet does is runs the network for the supercomputing conference. So not only the day-to-day Wi-Fi and wired needs of booths and all the convention attendees, but also we do bespoke builds for researchers and experimenters who come to show off demonstrations and things like that on the SC show floor. So in the past, we have, we like to claim we're the fastest temporary network in the world. Over the course of 2 weeks, we set up a network. We run this network as a production network for about 4 days and then tear it down in a day. We have brought anywhere from 2.5 to 4.5 terabits per second. Actually, I think Jason's year in 2018 was still our best, and I think that was 4.22 terabits per second into the show floor, into this convention center. And we do this in a new place every year. This year's coming up. It's going to be in Dallas, Texas. And like I said, we have availability on all our different teams, whether you want to do wide area networking, you're a wireless person, a fiber person, router person, whatever you may be, or even if you're interested in trying something new. If you're normally a router guy and you want to come do some layer 2 stuff or play around in the wireless world, we'll take you. It's a great experience. There's a lot of really great networking. I know, actually looking through the list, I know a lot of people in this. Hey, look, thank you, Adair. From my supercomputing experiences, you end up learning quite a bit. You get to play with contributors' latest and greatest technology. We have anywhere from 30 to 40. I think one year we even had $60 million worth of contributed gear, from the biggest names in the industry, Ciena, Juniper, Cisco, whatever. And you get to work side by side with their systems people, and it's pretty great. So that's my pitch. If you want more information on SciNet, hit me up, and we can. And I'll put a link, my email, and also a link. Thank you, Adair, and you can go there where Adair posted to see what teams are available and how to apply. And if you just want to talk about it, I'm happy to talk about it. And like I said, we will take, from the day one most junior engineer up to senior engineer. I promise you'll learn something. Pitch over.
Great. Well, thank you, Hans. Jorge, I think we'll throw it back over to you if we want to do the close down tasks and talk about surveys and such.
Thank you, Hans and Jason. Yeah, I want to thank everyone for coming today. Number 2, we want to ask you, your feedback is very important to keep improving our workshops, and we plan to keep doing this. So if you can take 5 minutes to complete this few questions survey for day number 2. Other than that, I think want to remind that all the material is being posted in our website, the workshop website. So the video, a link to the video of day number 2 will be also posted there and into a EPOC YouTube channel. That's pretty much, Jason, what I have. I don't know if there's anything else that you want to cover.
I don't think so. I think certainly I will thank everybody for their patience and their contributions over the past 2 days. As Jorge said, we're going to continue to think about ways that we can offer this material both virtually and potentially near the end of the year physically again. I know a bunch of people have been asking if we're going to attempt to do physical workshops sometime this calendar year. So Jorge and I have been talking about the way that we can try to do that. And we've been also working with some partners within the region to see if they have the ability to host the site. So we'll make any announcements about that via the cyber infrastructure list or the faster data list or any of the other lists that you may have gotten this announcement from. I guess I'll ask NYSERNet, Christy or Bill or Jennifer, if there's anything else that you guys would like to add.
I just would like to say thanks on behalf of the NYSERNet community for all of your hard work, at all those that from the trainers from EPOC and from the University of South Carolina. We so appreciate you bringing this to our community, and I believe that everybody got a lot out of it. So thank you so much for your hard work.
Thank you, Chrissy. Certainly the team that organized this workshop was fantastic. The NYSERNet people, Jason, EPOC, all the presenters, the grad students that work in the material. And from our side, that's it. Again, thank you everyone for your interest in these workshops.
Thanks all.
All right, and with this, we're concluding. Thank you. Have a good rest of the day.
Have a great afternoon, everybody.
Thank you. Have a good one.
Bye-bye.